Alright, today we're going to be talking about intermolecular forces. You're going to find this in your textbook in Chapter 13, Section 2. The main subtopics here are dispersion forces, dipole-dipole forces, and hydrogen bonds. So to kick things off, take a look at these standards. Intermolecular forces are kind of a foundational topic, but in terms of standards, the honor standard chemistry 2H, students know how to identify solids and liquids held together by van der Waals forces or hydrogen bonding, and relate these forces to volatility and boiling melting point temperatures. This is something that, again, it's an honor standard, but it's something that is going to be very important for us to know. Intermolecular forces, we're going to kick it off just talking about the difference between inter and intramolecular. Take a look at the words. Inter means between, so these are the forces between molecules. So forces that attract one complete molecule to another complete molecule. Intra means within. So what you're looking at here are the forces that hold a molecule itself together. Okay. As a quick review, take a look at this table. We have three intramolecular forces that we've discussed. First, ionic, covalent, and then metallic. We're not spending a lot of time with metallic bonds, but ionic and covalent are going to be used a lot for the rest of chemistry. Intermolecular forces, the forces of attractions that cause molecules to hold together. Once again, a key concept here is that these forces determine the state of a substance at a given temperature. So water is somewhat unique in that within 100 degrees it can be three different states. All intermolecular or bonding forces are stronger than intermolecular forces between molecules. So the forces that hold a molecule together are stronger than the forces attracting molecules to each other. Now for some Foursquare vocab, we're going to start with dispersion forces. Now dispersion forces, you may also see this term as van der Waals forces, as in the standard, or London forces. All the same thing. Yearbook refers to them as dispersion forces. These are weak forces created by temporary shifts in the density of electrons in atoms. As an example, you can see here, this would be a nonpolar covalent molecule. Typically, it's going to have the same charge on every contact point on the surface. But what happens is, because electrons are in constant motion, sometimes there's a temporary imbalance of where the electrons are. This temporary dipole that's formed, more of the electrons are on this side of the molecule, fewer are on this side, so we have a temporary negative and a temporary positive seen here. Now these temporary dipoles between molecules are going to cause a small electrostatic attraction. So you're going to have that partial positive to another molecule's partial negative. That's going to be the intermolecular force, that connects these. Next, dipole-dipole forces. Dipole-dipole forces are attractions between oppositely charged regions of polar molecules. So attractions between oppositely charged regions of polar molecules. So before, you were looking at typically nonpolar. For polar molecules, it's not a temporary charge. You have one atom where the electrons don't spend as much time because it's less electronegative. You'll have another atom in this molecule that is more electronegative, so the electrons will spend most of their time there. Because of this, these are stronger intermolecular forces, a stronger bond connecting the positive to the negative regions of these molecules. Next, we're going to talk hydrogen bonds. Hydrogen bonds are very strong dipole-dipole forces between atoms in molecules that contain hydrogen bonded with highly electronegative atoms. So in this case, you're always going to be seeing hydrogen, and typically you're going to see chlorine, fluorine, nitrogen, oxygen, the very, very electronegative atoms. In the image here, you can actually see the red ball indicates our oxygen. The white, these are the hydrogen atoms. So because hydrogen is polar, and it's very, very polar, it's going to have a very strong positive near the hydrogens and a very, very strong negative near the oxygen. Because of this, it can form these very, very strong dipole force bonds.